All right, let's look at the practical applications of electrolysis. You are absolutely going to be asked something with regards to this. First thing we're going to look at is the chloralkali industry. It's a very specialized industry that focuses on the production of chlorine gas, which is where the chlor comes from, and sodium hydroxide, which is where the alkali comes from. And hydrogen gas is produced as a byproduct, but it's a very useful byproduct. We use electrolysis and we use brine. Brine, of course, being a concentrated solution of sodium chloride. We do not use seawater because there's too many impurities in it. Okay? What we do use is the membrane cell. The membrane cell is the only cell that is legally allowed to be used anywhere. The first two cells that were made, the first one was a diaphragm cell. The diaphragm cell has asbestos in it, and the other one was a mercury cell, which of course has mercury in it, neither of which are good for us. The membrane cell relies on an ion exchange membrane, which is a fluoropolymer. It's patented, so you can't know the formula, and to separate sodium and chloride ions. What's very special about this membrane is it only allows Na plus ions, so it only allows the Na plus and specifically the cations to pass through the membrane and only to go towards the cathode. So the cations cannot go through the membrane towards the anode. So it's like a valve. It can only go in one direction. So the cell consists of two half cells separated by the membrane. The anode is filled with brine, okay, so filled with the salt water, and the cathode is filled with pure water. All right, the anode is still negative. The cathode is still positive. So the anode is positive. The cathode is negative. You've got to get this right. All right. So what happens is this. This is the sodium chloride solution. The sodium plus ions can go towards the cathode, which is what we want. In the anode part of it, where the brine water is, we will get the oxidation. So we will create the chlorine gas. At the cathode, now we've got sodium plus ions and we've got water. Water is a better oxidizing agent, so the water is going to be reduced, just like we did in the last one with the sodium iodide. The water is going to get reduced and it's going to create H2 gas. Okay? Why? Because water is a stronger oxidizing agent. So that's how we create the H2 gas and the Cl minus. But what about the Na plus? Because I said earlier when we started this that we would create sodium hydroxide. Well, look what happens. When I put the two reactions together, I have Cl minus and OH minus. The Na plus is a spectator ion, but it's a very important spectator ion. This is the only reaction that you will need to put the spectator ion in for. Becomes sodium chloride, becomes NaOH. That's where the Na plus got put. So we create three products that are incredibly useful, but of course they're quite dangerous. So we've got to look at the environmental impact. They're always going to ask you environment when it comes to this. We have the three products, hydrogen, chlorine, sodium hydroxide, are all hazardous. They all have issues. Hydrogen is very flammable and can react explosively, so it explodes quite easily. Chlorine gas is very toxic. In fact, chlorine gas was the basis of mustard gas, which was the first gas used as a biological agent in warfare, all right, and can cause extremely bad lung damage, or if not kill a human. Sodium hydroxide, of course, which we've done in acids and bases, it's a very, very, very dangerous base. Very dangerous base, okay? And it's one but it's got lots of uses. The advantages of using the membrane cell is that it doesn't really need to be cleaned very often or replaced. The parts don't need to be replaced. There's very little harmful impact on the environment compared to the other cells, okay, because the membrane is environmentally friendly. It's a polymer which can decompose. We get a very high purity of sodium hydroxide, which comes out, which is also important. And it's much cheaper than any of the other membranes, any of the other cells. So that's why we want to use it. So these are the advantages. Learn a couple of these, okay? Now we're going to look at electroplating. Electroplating is an application of electrolysis which allows us to put a thin metal coating on another object in order to either improve its appearance or to make it resistant to corrosion, to stop it rusting. This also works in the same way. I'm going to use a silver as an example, but it can be any metal. The important thing to remember here is the anode. All right, let's start with the cathode. The cathode is whatever we want to plate. A spoon, in your book there's a shopping trolley, a pair of shoes, whatever. It's whatever we want to coat. The anode is the metal we want to coat with. Silver, copper, nickel, whatever the case may be. So that's quite important. And in this case, it's silver. So anode is the metal we want to coat with. Cathode, the object we are coating. Okay? The electrolyte must be a concentrated solution that contains ions of the metal. So if I'm copper plating, it must be copper sulfate. If I'm nickel plating, it must be nickel sulfate. Okay, we don't want it to be another metal because we want to make sure that whatever we're coating with is being used. Okay, very important. So what happens? At the anode, okay, the silver gets oxidized. So the silver anode gets oxidized, creates silver cations. Those cations then move to the cathode. Okay. All right. So move to the cathode. When they move to the cathode, they then gain an electron. Okay. When they gain an electron, they go back to silver. When they're back to silver, it's been plated. Okay. So the whole point is we have silver, which becomes an iron. Once it becomes an iron, it goes back to being silver, but we have moved the silver from the anode to the cathode, and the silver can then bond on whatever the cathode's made out of. We good? All right. Then we can look at the decomposition of aqueous copper chloride. Chlorine gas is produced, so this is a solution. Chlorine gas is produced at the anode because the chlorine is oxidized and the copper is deposited on the cathode. The whole point is to separate the chlorine and the copper. This isn't a difficult one. Both of these are 2 electrons, so we're quite happy. That was the original solution. All right, it's just in iron form, and we can separate it into the 2. So the chlorine gets oxidized, it gives away its electrons, and the copper gets reduced because it takes the electrons. All right, let's talk about purifying metal. Now we do need to just quickly fix something here. Here, this should actually say that's a pure copper cathode, and this is an impure copper anode. Okay, so what happens is this anode is made up of a sample of copper, which we know has other metals in it, has other things in it other than just copper. We just want the copper. All right, so we make it into the anode. It's a little like the electroplating process. All right, in that we have a copper solution as well. So what happens is the anode gets oxidized. The copper becomes copper ions. Those copper ions then go to the cathode, see the cathode, go, oh, you've got the electrons I want, take the electrons that it wants, and becomes copper metal. So the cathode gains copper metal. It's already pure, so now we're just making it a bigger sample of pure copper. All the impurities don't join to the cathode, they drop to the bottom. So we get rid of the impurities. Okay, and the net cell's quite easy. It looks like electroplating, basically. So we can think of it as the same sort of process as electroplating. Okay, we have one more very, very, very important industrial process, and that's the recovery of aluminium from bauxite. Very, very important. Aluminium is found in a mineral known as bauxite, and it's an impure sample of aluminium oxide. So bauxite, impure aluminium oxide. All right, you have to know all these terms. Bauxite is not found in South Africa. It's found in Australia. So it's mined in Australia. It's imported to South Africa where we refine it, purify it, we then send it back to Australia where they make it into goods, and then we import the goods back to us. It's great. All right, so how does this process work? Well, number one, we first have to make the impure aluminium oxide into pure aluminium oxide. Okay, so the bauxite is treated with sodium hydroxide. It becomes aluminium hydroxide. The aluminium hydroxide is then heated. During that heating process, it becomes a pure aluminium oxide, which is called alumina. So impure, the ore that we mine is called bauxite. The pure aluminium oxide, so just Al2O3, is called alumina. We now take that alumina and we're going to work with it. So now we melt the alumina, but we first have to dissolve it in cryolite. The reason for this is that it reduces the melting point from 2000 degrees Celsius to 1000 degrees Celsius. All right. And that is very important because it reduces costs, reduces energy, it makes it a little less environmentally unfriendly. This process uses a ridiculous amount of electricity. Okay, and of course that means because in South Africa we create our electricity from coal power stations predominantly, all that electricity is environmentally unfriendly for us. All right, now we have pure Al2O3, which has been melted. It's become a liquid. That molten alumina cryolite mixture is then placed into the reaction vessel where we can pass an electric current through it. The anodes are carbon rods, okay, and the cathode is the steel casing. So it's not a rod, it's the actual container that it's in. So if we look here, here's my steel casing, that's my cathode, okay. There's my carbon anodes. This first part here is the cryolite molten alumina solution. All of this is the liquid aluminium that's coming out. It's been done at such a high temperature that it comes out as a liquid. Okay, so the aluminium ions get reduced to aluminium metal. That's the whole point. We want aluminium. Okay, very important. So we've got that. Now what happens, okay, is that the oxidation is where the anode is, and we get oxygen gas. But if you look here, I'm telling you we get carbon dioxide, not oxygen, because of this. The high temperature causes the oxygen that's produced to react with the carbon anodes. That creates carbon dioxide and C carbon monoxide. This is what is also an issue. They can't prevent that. They actually cannot prevent that from happening. All right, it's the best way they can do this. So it can't prevent it, but the carbon gets used. It also means that the carbon electrodes need to be replaced because they're eventually going to disintegrate. They're going to disappear. Okay, so we get the aluminium, which goes to the steel casing at the bottom because it goes to the anode where it's going to, goes to the cathode where it's going to get reduced, and then we can take it out. And then the oxygen, which forms, because it's oxidized, okay, the O2 is oxidized, it goes to the carbon anodes. Those anodes then react with the carbon, giving us carbon dioxide and carbon monoxide. There are a couple of issues here. The process consumes a ridiculous amount of electricity, which also makes it quite expensive. Okay, CO2 is released as a waste product into the atmosphere, which of course is a problem. The fluoride emissions that we get from the cryolite as it breaks up during the electrolysis is also very, very important, damaging to us. Also, due to high production costs, recycling of aluminium is much more desirable because it's cheaper and easier to recycle aluminium. However, we can't recycle it fast enough because aluminium is like a super metal at the moment, okay? It's used for so many things. It's incredibly important metal for us. All right, so please, once we get to a point where we can recycle aluminium fast enough, we'll be okay. But at the moment, we can't. So we're using a very unfriendly, environmentally unfriendly process to create a very, very useful metal. Okay? In the next video, we'll start looking at galvanic cells.